Okay guys, so today just gonna make sure that I go through all the theorems of Euclidean geometry, right? Why? Because I believe they're important and we need to know all of them. So the first theorem is Theorem I, right? Theorem I, we have a diagram that looks like this. So let me draw the circle nicely. We have a circle. Just assume that this is a circle, right? And you're gonna have something that looks like that, and then you're given that this is perpendicular. So let's say this is your O, which is your center. So let's say this is your center. You just assume that this is the center, and you have this point here, and this point here, whereby this is A, this is B, this is C, right? And so you are given that OB is perpendicular to AC, right? And you are required to prove that AB is equals to BC. So that is theorem 1. So the first thing you're going to do is, in your proof, is you're going to start by constructing. So you're going to construct line OA and OC, right? So you're going to construct line OA and OC like that. Then once you've done that, now you have triangles. So you have triangle OAB and triangle OBC. So you have two triangles, né? So the first thing you have to do here is you need to compare these triangles, right? So that's how you're going to prove the theorem. You need to compare the triangles. So what you're going to do is you're going to say in triangle OAB and triangle OBC, right? The first common thing about these two triangles is OA is equals to OC. Reason for that, it's radii. So they have equal radius. So this radius is equals to this radius, right? And then another thing that you can take from this is OB is equals to OB. Reason for that, it's common side. So this is the common side here. So let me just write one line. And then another thing that is common here is, another thing that is common here with these triangles is this angle here of 90 degrees, right? So let's say this is B1, this is B2. So you can say angle B1 is equals to angle B2 is equals to 90 degrees. So reason is given. So you're given these angles here. So now you can conclude and say, fine, you've proven a side, and you've proven an angle, but this angle is 90 degrees, and one side of these two sides here, it's a hypotenuse, right? So you can simply say, therefore triangle OAB is congruent to triangle OBC. So the reason for that is right hypotenuse side, because you have your right angle, your hypotenuse side that you've proven, and your common side, right? So that is going to be your theorem 1. So the whole purpose of you was to prove that they're equal, right? So now you can confirm that, therefore AB is actually equals to BC. So this is equals to that. So now you've proven that by doing congruency, right? So another thing that you can do is theorem 2, right? Theorem 2 is the opposite of that. So let's say, for example, you are given your circle. Let's say this is a circle, and more or less the same thing. and then this is your O. Let's say this is your center. Just assume that this is the center, and then you have your points here and here, which this is your A, this is your B, and this is your C. So now in Theorem 2, you are told that AB is equals to BC, right? So you are given that AB is equals to BC. So you're required to prove that OB is perpendicular to AC. So that's what you're required to prove now. So what you're going to do is this. You're going to construct, that's the first thing. So for your proof, you're going to construct line OA and OC, right? So you're going to construct it here. Then it will form your triangle. So now you're going to have your triangle OAB and triangle OBC, right? So now you're going to compare these triangles using congruency. So the first thing you're going to do is you're going to say OA is equals to OC. Reason for that is radi. So this side is equals to this side. Reason is radi. And then OB is equals to OB. Reason for that, it's common side. So this side here. And then AB is equals to BC. So for that, you are given. So therefore, the two triangles are congruent. So triangle OAB is actually congruent to triangle OBC. So the reason for that is you've already proven this side, and this side. So you've proven sides, right? So you've proven side. So you just want to say side. So therefore, this concludes now that actually OB is perpendicular to AC. So you're done with Theorem 2 if you do this here. So now let's go to Theorem 3. So it's very important that you know these theorems. You don't have to memorize, you don't have to cram them, sorry. You can memorize them. You can try to do what I'm doing here, which is to just walk around them. Oh no, this circle is not nice. So let me do Theorem 3 now. Just trying to draw a nice circle. Okay, fine. Let's say this is a circle. So this is Theorem 3. So in Theorem 3, you'll have something that looks like this. So it will look more like a kite, right? So it will look something like this. And let's say this is your O, and this is your A, this is your B, and this is your C, right? So here you're given points A, B, C, and center O, right? And we are required to prove that angle BOC is equal to twice angle BAC, right? So you're required to prove that this angle here is twice this angle here, right? So the first thing you're going to do when you prove is this. So your proof, you are going to construct line AO, right? So you're just going to construct a line that goes something like this and probably ends here, which will create your A1 and A2 and your O1 and O2 like this. So now let's try to look on our left hand side here. So you can say angle A1 is equals to angle B, right? So let's see, angle A1 is equals to angle B. So the reason for that is that our AO is equals to our OB, which is radi. So if you check clearly, this side here and this side here, they're actually equal. They are the radius of the circle, so therefore it will give you equal base angles. So that's the first thing you're going to identify. The second thing that we can identify here is that angle O1, which is this one here, it's equals to angle A1 plus angle B. So the reason for this is exterior angle of a triangle. So if you remember clearly your exterior angle, so if you say you're having a triangle like this and it has an extension here, so this angle here and this angle here will give you this angle here. So that is your exterior angle of a triangle. So similarly, meaning that you're going to do the same thing on your right hand side now. So you're going to say angle A2 is equals to angle C. Reason for that is that our OA it's equals to OC, which is a radii, as I said. So this side here and this side here are equal, creating equal base angles. And also our O2 is equals to angle O2 plus angle C, right? Reason for that is exterior angle of a triangle. Fine. So now you're having this, and this. So how about now we combine angle O1 plus angle O2 equals to, so what is O1? O1 is this one here, which is angle A1 plus B, right? Close the brackets plus, what is O2? So O2 is this one here, which is angle A2 plus C, right? But you need to remember, but we said angle A1 is equals to B, angle A2 is equals to C. So we said that here and here, right? So we have to substitute that. So wherever we see A, we're going to put B. Wherever we see A2, we're going to put C, right? So we'll continue to say angle O1 plus angle O2 is equals to, so wherever we see A, we put B. So it's going to be B plus B. Oh no, we have to do the vice versa now, because we're trying to prove for A, not for B, right? So wherever we see B, we have to put A. Wherever we see C, we have to put A, because we're trying to prove the angle of A. So it's gonna be A1, angle A1 plus angle A1 plus angle A2 plus angle A2, which angle O1 plus angle O2 is equals to twice angle A1 plus twice angle 2, like that. So then what's going to happen is this. So now you have twice, but you need to note that the combination of O1 plus the combination of O2, right, which is this one here, it's the combination, gives us angle BOC, right? So it gives us this here, it gives us this here, this angle here, right? So the combination gives us this angle, and angle A1 plus angle A2 gives us BAC, right? So we can simply substitute that. So we're just gonna do this quickly. So what we can do is this. we're going to say, instead of writing this O1 and O2, we will write this part here. Angle BOC. So let me correct here. Angle BOC is equals to twice. So here we're having twice A and twice B, right? So twice A plus A1 plus A2, right? And then I said, instead of writing A1 plus A2, you simply write this. So it's going to be BOC is equal to twice BAC. So now you're done. You've proven Theorem 3. So now let's do Theorem 4, which is created by Theorem 3. So Theorem 4, let me draw a circle. Let's say this is the circle, and Theorem 4 looks like this. And then so let's say this is A, this is B, this is C, this is D, like that. And this is your O, which can be O1 and your O2 here, right? So let's prove Theorem 4. So what's happening here? What we can see is that angle O1, which is this part here that is outside, angle O1, it's equals to twice angle C, which is this one here, right? So the reason for that, it's angle at center. So that's the reason for Theorem 3. So I forgot to mention that for Theorem 3, you need to note that angle at center equals to twice its circumference, right? So that is the reason for Theorem 3. Just to go back here, so this is angle at center, it's equals to twice its circumference, and then angle O2, which is this one here, it's equals to twice this one here. So O2 is equal to twice angle A. Same reason, angle at center equals to twice its circumference. So now that we have this, but angle O1 plus O2 is equals to 360 degrees, right? Why? Because it's a revolution, so the entire O1 plus O2 gives you 360 degrees. So what you're going to do is you're going to say, okay, fine, angle O1 plus angle O2, it's equals to, so what is O1? It's twice C, so it's going to be twice C, plus O2, it's twice A, so it's going to be twice A. But what did we say about O1 and O2? They equals to 360 degrees, equals to, so the 2, you take it out, you have angle C plus angle A, and then divide by 2 both sides. We have 180 degrees is equals to angle C plus angle A. So meaning that the angle C plus the angle A added together will give you 180 degrees. So the reason for this one is opposite angles of a cyclic quad are supplementary, right? So opposite angles of a cyclic quad are supplementary. Let's go to Theorem 5. So for Theorem 5, some books are different. I'll just say this is Theorem 5. It's up to you whether you agree with me or not. So let's say you have something like, something like this, right? And I'm saying this is Theorem 5. So when you have a quadrilateral like this, if you can see clearly, this was formed by Theorem III. If you remember, Theorem III looked something like this, and it was like that. So what happened here is this small portion here, this small portion moved to the circumference instead, creating Theorem V. So that's why I say Theorem III forms Theorem IV and Theorem V. So here, what we need to note is that we are having this chord here. So this chord produces an angle here. And then the same chord produces an angle here. So because these triangles, let me draw this triangle so that you can see clearly. So because this triangle here, this triangle, and this one here, they share the same chord. They share the same chord, therefore they'll have equal angles here at the circumference due to them sharing the same chord. So meaning even here, if this is going to be your chord, therefore the angles here will be equal. So the reason for this theorem here is angles on same segments. So this is the reason for this theorem. Or I can just write subtended by same chord. So if you write this, it should be correct. Now let's go to Theorem VI. Theorem VI. Okay, fine. Theorem VI goes like this. So we having, let me see, I'm not forgetting. So we're having a circle, right? Okay, let me draw it nicely. So we're having a circle like that, and then you have tangents that go like this, and then a line that goes here to the center, and then a perpendicular one here, perpendicular one here. So this is your O, 1, 2, and this is A, this is P, this is B, right? P1, P2. Fine. So you're having something that looks like this, which this is your tangent and this is also your tangent, right? So in Theorem VI, so this is the, Theorem VI. So we also need to prove, so we are required to prove in Theorem VI, we are required to prove that AP is equals to BP. So basically this tangent, you are required to prove that these tangents are equal, right? So the first thing you're going to do is you're going to apply your congruency again. So you're going to look at triangle OAP and triangle OBP, right? That's the first thing you're going to do. So in those triangles, you're going to compare them, and then once you've compared them, then you can conclude that AP is actually equals to BP. So the first thing we can see from these two triangles is that angle A is equals to angle B equals to 90 degrees, right? Reason is given. We are given that. And OA is equals to OB. Reason for that, it's radi. So this side here, it's equals to this side here because they are radius. And then another part is OP is equals to OP, which is a common side. This side here is common. So now you've proven you've proven two sides, 1 and 2, and then you've proven an angle. So therefore, triangle OAP is congruent to triangle OBP. So the reason for that is right hypotenuse side. Right? So this concludes that AP, tangent AP is equals to tangent BP. So now we're done with our Theorem 6. Let's go to our Theorem 7. So Theorem 7 looks something like this. So it's Theorem 7. Let's say this is my circle. Oh boy, let me redraw it. Okay, fine. So let's assume that this is the circle. Let's assume that this is a circle. Then, and you have your tangent that goes like that. And then you have something that looks like this. Right? And let's say by labeling, this is your A, this is your B, C, and D. So it's A1 here, and then yeah. So you are required to prove that angle C1 is equals to angle A. So this angle here is equals to this angle here. That's what you are required to prove. So the first thing you're going to do is this. You're going to construct COK, right? So which is going to be your diameter, basically. So you're just going to construct the diameter going up like this. So meaning somewhere here it's going to be your O, and then this is going to be your K. And then you're going to extend your line. So extend KA. So meaning you're going to extend the line going in that direction. So if you can see there's Theorem 6 here. What do I mean by that? Is that this angle here is equals to this angle here. So that is your Theorem 6. But anyways, we don't look at that for now. What we can note is that since we said that this line is a diameter, COK is a diameter, that tells you that an angle at this circumference, this angle here, it's 90 degrees. So that's the first step. So angle A, it's equals to 90 degrees. Reason is KOC is a diameter, or you can simply say angles on semi-circle, basically. So yeah, it's 90 degrees. And another thing that you can confirm is that this part here is also 90 degrees. So angle C is 90 degrees. Reason for this one is that the diameter of KOC is perpendicular to the tangent of CD, basically. Right? So we've proven that these two are 90 degrees. And what we need to note is that this angle here is equals to this angle here. So let's say this is A1, this is A2, this is C2. So we can simply say angle A1 is equals to angle C2. Angles on same segments, right? Angles on same segment. So if A1 is equals to C2 and the entire A is equals to the entire C, therefore this concludes that so if angle A1 is equals to angle C2 and angle A is equals to angle C is equals to 90 degrees, therefore it concludes that angle 2 is equals to angle C1 like that. So it concludes what we are trying to prove. So it concludes that this side here is actually equals to this side here. So the reason for this one is that tan chord theorem. So that is the reason for this Theorem 7 here. Done for now. Please make sure you subscribe and comment down below.